one of the first things I want to talk to you about this evening, calculus, differentiation, integration, calculus, rates of change. This comes up, I think, nearly every single year. I don't think, TJ, I've ever seen rates of change not come up, actually. It's so consistent on the exam.
Yeah, but it's also like calculus comes up as like part one. So like they even start changing this project maths. Like they stick in calculus and it's a part of like a trig question. Or it's a part of like a bigger, like whatever style of question. Like they'll put it into every part of it as well. They'll give this massive wordy question, and you're like, oh my God, it's using algebra, trig, calculus. Like, get ready. That's going to happen, I guarantee.
And calculus is a really important one as well, guys, because it's used in applied questions for simply this reason. Isaac Newton invented it, world famous physicist, right? It's physics, it's not fucking maths, it's actually physics. So it's in the most applied questions. If you've got a big applied question, you've got a cone with something flowing into it, you're going to differentiate in that question. I can guarantee you right now. Let's go through some of this, okay? Right. Where are we? Okay, let me do a little bit of organizing of my screen here.
Perfect.
So
I'll also run a little poll, Niamh, around how everyone's getting on with the mocks, how they're feeling out with the mocks. I'm going to launch that poll here. 3, 2, 1, go. How are you feeling with the mocks? 107 of you there. How are you feeling about it? It's a little poll. Give me a sense of it. Scared, scared, scared. 90% are scared. 92% are scared.
Few 4% confident, if you don't mind. Go on then. Go on then, lads. Yes.
Excellent. Brilliant.
Amazing, guys. So, guys, just a quick thing, right? So calculus, oh, let me just go through the notes I'll give you quickly, right? So the very beginning, we've got just paper one. We're going to do paper one topics. It's the start, okay? How long we spend each question, how long I want you to look through the paper, blah, blah, blah. That's all the information there. You can go through it in your own time. I've got a couple of things, area and volume, always really bypassed by people, right? Because it's one of those topics that's like, oh, sure, like, yeah, I know how to find the area of a shape, right? Curved surface area versus flat surface area, very often mixed up. I want you to go through that. Trapezoidal rule, quite an important one. If I have time at the end, that's where I'm going to be heading to, okay? For now, I want to talk to you about calculus, okay? Differentiation, integration, right? Here's our basic rule, right? Y is equal to x to the n, dy dx, when you differentiate it, is n x to the n minus 1, okay? Some other things that you absolutely need to be super comfortable with, okay? Product rule, quotient rule, chain rule, and differentiating these things. These things are all in your log tables, but you need to know how to read your log tables as well. No good having them in front of you, don't even know how to use them, okay? These are really, really, really important, okay? Again, I'm not going to go through all these things right now because we don't have time. I'm going to go through some of the more conceptual stuff, okay? Okay, what the hell is differentiating, okay? What are we actually doing when we differentiate something? What we're actually finding, guys, is the rate of change of one variable with respect to another. dy dx means how does x change when y changes? How does y change when x changes? Okay. Another way of thinking about that is finding the slope. Okay. If I look at how steep this thing is, right? This is our x here, this is our y here. And I think about, well, what's the slope of this line? Like, how steep is this line? Well, if the line was up here, then sure, the y gets really, really big and not that much x has gone. As x gets big, sorry, y gets big very, very quickly. But if I had a line like this with a much smaller slope, well, y doesn't really grow much as x gets bigger. Okay, so that's what we do when we differentiate. We find the slope, or we find the rate of change. We find how one thing changes with respect to another. Let me tell you a really important applied example of this, right? Let's say we've got something like this. Say some kind of function where we have distance here and time here, right? And it goes something like this. If I was to differentiate this function, right? So your y is your distance, your time is your x, okay? dy dx would be the rate of change of the distance with respect to time. How much distance passes in how much time? Guys, can you give me a guess, right? Can you give me a guess? What do you think that actually is? What do you think the rate of change of distance with respect to time is? Alex Harbison, what do you think that is? Just a guess. What do you think dy dx is here?
I'm not entirely sure. We haven't done the chapter. Apologies.
That is absolutely fine, right? What it is, guys, this is speed. The rate of change of distance with respect to time, speed. Okay, so when you differentiate something, you're finding physical quantities. And this particular example where you're differentiating distance with respect to time and that being speed, that is a really, really important one that you do need to know. Okay, that does come up in questions. Okay. Some other key points that I want you to be very, very comfortable with, okay, is how to differentiate from first principles. Guys, this is how to differentiate something by using the formula from differentiation. This is the formula, if you might recognize it, lim as h goes to 0, f of x plus h minus f of x all over h, okay? Differentiating from first principles, make sure you know it. Finding local maximum, finding local minimum, finding the rate of change with respect to one variable with respect to another, okay? What I'm going to go through now is finding the local maximum or local minimum of a function, okay? Let's have to do this now. Okay, guys, so remember I was saying before, right, that if you differentiate something, you're finding the slope, okay? So for example, let's say I've got a function that's like this. Then if I differentiate it, then I'm finding the slope at any given point of that function, right? I'm finding the slope here, or I'm finding the slope that's here, or I'm finding the slope that's here, or here, or here, okay? Now, whenever I'm doing the local maximum or local minimum, that's whenever the graph is turning. That's the turning point of the graph. Here's the minimum of this graph, right? If it was a opposite way around, then our maximum would be here. Guys, the slope at this point, it's just a horizontal line. Does anyone know what the slope of a horizontal line is? Ray Snape's great name. Do you know what the slope of a horizontal line is?
0.
0. Awesome. Banging. So cool. The slope of a horizontal line is 0, guys. So if you're trying to find the local maximum or local minimum, then you let the differential, equal to 0, okay? Because the slope at that point is 0 because it's turning. So it has to be flat. Okay. Is my pen gonna work? Yes, it is. Okay, so let's do it. Let's differentiate this one. So dy dx. Okay, guys, we're gonna give a go differentiating this using our rule that I was showing you earlier. Nicole, can you differentiate 3x squared for me? Can you give it a go?
6x.
Unreal, Nicole, well done. 6x, exactly, perfect. Differentiating minus 2x, I'm left with minus 2. 8 is just going to leave us with 0. So we got 6x minus 2. If I'm trying to find the local maximum or local minimum, I'm letting it equal to 0. So I'm going to solve for x now, guys, okay? So we're going to end up with 6x. I bring my 2 over to the other side, equal to 2. Divide through by 6. X is equal to a third. Okay. So we're saying that this minimum or maximum is happening when x is equal to a third. Okay. But how do we actually figure out if it's a local maximum or local minimum? Right? How do we figure out if it's a min or max point? I mean, if you've got a quadratic function, yeah, you can kind of tell by the shape of the quadratic function. But let's say I had, a cubic graph or something a bit different. Let's say I've got a graph that has a maximum and a minimum, right? How do we find out which is the max, which is the min? Guys, we double differentiate. We do a double differentiation. What does that look like? dy squared over d squared dx squared, dx squared. We differentiate it for a second time. So let's differentiate 6x minus 2 for a second time. Okay, so we've got d dx, 6x minus 2. I can't get my white pen back, so you're going to deal with my green pen. Apology, guys. So differentiating this. Can you differentiate 6x for me, Grace? Grace's iPhone. What would that look like if I differentiate 6x?
Just 6.
Just 6. Unreal. Well done. Just 6. Exactly. Now, guys, if d squared y dx squared is greater than 0, then we're looking at being a local minimum point. A local minimum. I'm going to try with my white pen again. Yes, it's working this time. If we have that d squared y dx squared is less than 0, then it's a local maximum. Okay, I'm going to ask 2 questions. Can I have a raise of hands on your emoji? Can you give me raise a hand emoji if you've ever heard of this before, of this local maximum, local minimum thing? Right. What about the second derivative. The way we use it to tell if it's a maximum or minimum. Yeah, people have heard of this. Okay. Okay. Stop giving me reactions. I have another question. Does anyone know why? Does anyone know why that whenever d squared y, d squared x is less than 0, it's a minimum or a maximum? No hands. No hands. Right. Good. This is something, honestly, this is something that no one ever tells you, and I don't know why. And it's so important to know. Okay. Let me just get this done. Sorry, my laptop's freaking out with like 300 people on this Zoom. Okay, so guys, this is why. Okay, remember I was saying to you before, but stick with me. This is a little bit conceptual, but it's quite fun. So stick with me. All right. Remember I was saying to you before, I was like, well, when you differentiate something, you find a rate of change. You find the slope. So the first differential, right, dy dx. I'm going to zoom up here. Maybe just get a little bit closer. Is the slope at each point. Okay, it's like the slope at each point. It's whether, you know, it's decreasing or increasing with respect to each variable. Okay, it's like the slope like this at each point of this graph. That's dy dx. But then d squared x, d squared y, dx squared, on the other hand, d squared y, dx squared, we're finding the rate of change of the rate of change. The slope here, right, it's positive, 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 but then it becomes negative, 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 and then the slope becomes positive again. So when it's a maximum point, the slope goes from positive to negative. So that rate of change is negative because it's going from a positive to a negative. So at a maximum, it's a negative. When it's going from a negative to a positive, when it's going from negative to a positive, it's increasing, and that's at the minimum. So at the minimum, it's positive. You're looking at the rate of change of the rate of change. Okay, this is why it's flipped, like this is why it's backwards. The maximum is negative and the minimum is positive. Okay, and that's the reason why, because you're looking at the rate of change of the rate of change. Okay, show of hands, does that make a bit more sense now why that is the way it is? Even a little bit? Oh, so nice, guys. Awesome, so cool. Okay. Okay, I'm very, very quickly going to run through how we integrate. I'm just going to show you the rules.
All good, Niamh.
Thanks. Just going to show you the rules, right? And then we're going to do an exam question on this, okay? A really nice exam question that I spent ages trying to pick, and it's perfect for our purposes. Okay. So, guys, rules of integration. Integration is the exact opposite of differentiation. Okay. And when you integrate something, by the way, what you're actually doing is you're finding the area under the graph. If you integrate a function, you're actually just finding the area under that function. Okay. That's why I was kind of being like, look at the trapezoidal rule. It's really important. That's kind of where it starts to come up. Okay. Try to relate those two things when you're going through the notes. But that's what you're doing. Now it's the opposite of differentiating. So our rules are basically opposite. If y equals x to the n, if we integrate it, we end up with x to n plus 1 over n plus 1. And very importantly, we have our plus c. We only have our plus c when it's an indefinite integral. That means there's no numbers here at the top and bottom of the integration sign, guys. That's when you put the plus c. Okay, you put the plus c when you don't have a number on the top and the bottom of that integration sign. Really important, okay? Definite integral, a little bit different, okay? You do have the numbers at the top and the bottom this time. And you don't put the plus c. But what happens instead is that you sub those numbers in for x. Do you see the way they have that there? We sub those numbers in for x, and we take a away from b when we put it in for x, okay? With this minus sign in the middle. Okay. Okay, using this, guys, let's do the first part of this question. Okay, guys, I want absolutely everyone giving this a go. And if you have to get the answer, you can stick it into the chat, okay? So I'm not going to worry too much about this waffle at the top. It actually doesn't even matter that much for the question. Classic leaving cert, trying to confuse you with a lot of words. So the volume of the pyramid is the integral from h to 0 of s of x. And s of x is given by this function. Okay. Using integration, find the volume of the pyramid. Okay, the volume of the pyramid is integral of this. So integrate it and find the volume of the pyramid. Can everyone try that for me now? Everyone give that a go. Okay. Okay, guys, let's just carry out this bit of integration, okay? So what do we have? We're integrating from h to 0, the function x squared c squared over h squared. I'm not going to worry a tiny bit about the c and this h here, guys, okay? Because we're integrating with respect to dx. So my c and h, we could just treat them as numbers, we can just treat them as constants, whatever. So let's focus on this x to the power of 2. What do we do when we integrate, guys? We add 1 to the power and we divide by that power. We end up with this, c squared, h squared, okay? Now we're going to sub in h for x and 0 for x and take them away. This is equal to h cubed over 3 c squared over h squared minus 0 cubed over 3 c squared over h squared. 0, everything multiplied by 0, we can just forget about it. Squared is going to cancel here, and we end up with h c squared over 3. Okay? Just integrating the first part of the question. Now, this is the part I want to spend a little bit more time talking about. This is your related rates of change question, guys. This comes up so often, okay? This is a really want everyone to go away feeling a bit happier about this, because this is something I always see people tripping up with. So in these related rates of change question, you're told one rate of change. You're told, 1 dy dx. You're asked to find one, and then you have to create another one. Okay, stick with me. I'm going to go through slowly. In this question, we have x starts to increase. You can forget these notes, but I'm going to go through these in a second. X starts to increase at a rate of 3 units per second. Okay. Okay, so that means I've straight away been given a rate of change. 3 is equal to dx d what? Dx d what? Emma, what do you think? Maybe Emma can't hear me. Emma Bruin, what do you think? Dx d what? 3 is equal to dx d what?
D3.
Well, it's gonna be a letter, right? This is I'm so glad you didn't actually get this, Emma, because this is the thing that I was trying to point out that everyone struggles with. So thank God you didn't get it. Guys, right. This is what I always see students struggling with, okay? Is that what we want to do is we're trying to find we've been told one rate of change, that 3 is equal to some rate of change, but people often find it very difficult to know what that rate of change actually is. Like, is it dy dx, is it dx dv, is it dx whatever. Okay, it says x starts to increase at a rate of 3 units per second. Now I'm going to tell you right now that I know that this is dx dt, where t is time. The reason I know that is because they literally have told me in the question. They've told me, because they said it's a rate of units per second. Per second, units per second, x being some units per second. Therefore, it's differentiated with respect to time. Look, whenever they give you these numbers, they're going to say, oh, meters per second. They're going to say, kilometers per meters cubed. They're going to tell you exactly what they've differentiated with respect to, because they give the units of whatever they're giving. Physicists and people that are studying physics and things are very comfortable with this concept, because we have to use units a lot more in physics. Okay, does that make sense, guys? Can I get hands if that concept makes sense? Because it's so important. So cool, so cool. Okay, so we got 3 is equal to dx dt. It says find the rate of change of s of x with respect to time. The thing that we want to find is ds d what? What are we trying to find? ds d what? Maria Moras, what do you think? Maybe Maria can't hear me. Okay, guys, find the rate of change with ds with respect to time. Again, they've told us in the question. Find the rate of change with respect to time. We're looking for ds dt. We're looking for ds dt. Okay. Okay, at an instant when x is equal to half, the perpendicular height of the pyramid. Okay, guys, we were told at the beginning of the question, the perpendicular height of the pyramid is h. Okay, so we're defining this for whenever x is equal to a half h. Fine. Give your answer in square units per second, blah, blah, blah. Okay, so we are looking for ds dt. We know dx dt. So now I'm trying to figure out what should I multiply this by to get back ds dt. Okay. Can you everyone take a minute to think about what they might multiply dx dt by to get back ds dt? Grace Hayes, what do you think? Guys, if you can, oh yeah, go ahead, Grace.
dt ds, or like
Nearly. We want to keep the dt, right? Because we have that there, so we don't want to get rid of that dt. But
dt.
you're right. We need a ds. We need a ds at the top. So let's put that in straight away. We want to keep this dt, but we want to get rid of the dx. So guys, we're going to put that down here so that they cancel. Does everyone see that? You can treat, right? Okay, I mean, you're always told so many times in school, like, oh yeah, differentials aren't fractions, they're not fractions. Yeah, they're not fractions, but you can treat them mathematically as fractions. Really, you can. Like, you can manipulate them in the same way you manipulate a fraction. Okay, they're not fractions. Yes, if you're using them in an algebraic setting like we are now, treat them as fractions. Go ahead, so fine to do that. Okay, so we've multiplied by ds and dx because we want to get rid of that dx and we wanted a ds. Okay, so what are we going to do next? We're going to find ds dx. Okay, so we were told at the beginning of the question, that s of x is equal to x squared c squared over h squared. So ds dx, differentiating that, guys, differentiating with respect to x, we're going to get 2x c squared over h squared. Okay. So now we can multiply it in. So then we have that ds dt. Sorry, I'm struggling to get a pen here. Okay, that makes it a bit smaller. Okay, we have ds dt is equal to dx dt, which we're told is 3. Okay, we're told dx dt is 3, multiplied by 2x c squared over h squared. Are we done? No, guys, because it asked us to do it at the instant that x is equal to a half h. So we just have to sub in a half h for x. We've got 6 a half h c squared over h squared. And we end up with, these cancel, 3 c squared over h. Okay. Okay, guys, do those kind of questions, are they a little bit more clear now? A little bit.
I might unshare you, Niamh, a second, because given a context for you late joiners. So guys, full screen, I'll unshare you, Niamh. So context. We're doing a class, an hour, 10 minutes long. We've done calculus there because it's so integral to all parts of the question. We're going to do how many more topics, Niamh? Do you want to do 3 or 4 more?
Yeah, at least 2 more, hopefully.
2 more. Perfect. We're going to keep going and we're going to use a chat for a few more. So just give you context, we're nearly there, about 10 past 6, and we'll go on to the tests. All right. All right, Niamh, we'll get you go again.
Okay. Guys, I'll just say that if you like, if whatever I just spoke about didn't really sink in just then, like, so normal and fine, but look at the recording and go back at what I said, especially about being able to tell what it is from the units. Okay, I have, honestly, that will demystify a lot for you. So listen to that back, what I said. Okay. Complex numbers. I want to talk about complex numbers. Such an important topic, such an interesting topic as well for me. Big thing in my research. I use a lot of complex numbers.
Engage the room, Niamh. How does everyone feel about complex numbers? Into the chat. How do you feel about it? Good, bad, indifferent? Do you like it? Yes, no? How do you feel about it? Into the chat. Bad, like them, confusing. I'd say confusing. A lot of goods. All right. Let's see how you get on this one.
A lot like me then. A lot like me. Guys, complex numbers are a really, really strange topic, really, really strange concept. I mean, what are we talking about? We're talking about a negative square root. I mean, that the actual concept of that makes absolutely no sense. And the guy that came up with them, he just came up with them as a game, was like, oh, feck it, sure, I'm just going to make this up and pretend that this is true in maths, and ended up applying to like so much stuff. I mean, people build helicopters using complex numbers. It's the weirdest thing. So the reason you guys have to do it in your leaving cert is that it actually applies like wildly to the world of like engineering and maths, which you would never really expect. But anyway, that's not that useful for your mocks, is it? Feck's sake. Right, so let's talk about really what you're going to need to care about more. What, guys, what is I? Go on, someone tell me what's I. Nico Bovida, what's I?
We mightn't have it there. That's an easy one to text in as well to the group. Anyone want to text into the chat there? What's I into the group? Into the
What's
chat,
I?
sorry. Imaginary
I don't
number.
think we've done them.
You haven't done
Um,
complex numbers. Okay, not to
no.
worry. I wouldn't expect you to know what I is then. Yeah, guys, text me in the chat. But does anyone know what I is? Square root of -1. Unreal, guys. Square root of -1. Yeah, exactly. So this is something that doesn't, when you put that into your calculator, you're going to get a mathematical error. It doesn't make any sense because when you square something, then you multiply two things together. If you get two minus numbers, you get a positive number. Two positive numbers, you get a positive number. So taking the square root of negative number, it doesn't make any sense. So the square root of -1 is I. If I said that if I give you a complex number z is equal to 3 plus 2i, can anyone type into the chat the conjugate for me? What is the conjugate of that? What's the conjugate of 3 plus 2i? Yeah, awesome, guys. Awesome. 3 minus 2i. To get the conjugate of a complex number, guys, you change the sign in front of the I. What is a huge mistake I get seen being made all the time is people, whenever you see something like this, like 5i plus 3, what would the conjugate of that be, guys? Send that to me in the chat. Let's see if I have anyone making this mistake. 5i plus 3, what's the conjugate of that? Oh, I'm trying to catch you out. You're all too fucking good. Exactly, guys. You're always changing the sign of the I. You're always changing the sign of the I. What you often see people doing is saying this 5i minus 3. And some of the best students in the world will do this, guys. I have done this in the past, and it's just that you, in a panic of an exam, you just straight away put the minus in front of the, not in front of the imaginary number. You always have to put the minus sign in front of the imaginary number. Amazing. Okay. Some things that we definitely need to know how to do in this topic, okay? Adding and subtracting complex numbers. You need to know how to do this off the top of your head, back of your hand, okay? How do we do that? We add like with like, okay? You add the normal numbers with the normal numbers. You add the imaginary numbers with the imaginary numbers. You don't mix them, okay? Multiplication, to multiply them, you multiply them all together, but you just have to make sure to remember that I squared is -1 because you've got root I by root I is -1. You've got I cubed is minus I. Okay, those are just two important facts to do your multiplication. Division now is a bit more tricky. Division could be a little bit more tricky. Let's say we've got something like this, 3 plus 2i over 5 minus I. Guys, when you're dividing by complex numbers, you don't want to have a complex number at the bottom, basically. If you've got an imaginary number at the bottom, we don't really know how to divide with complex numbers, and it messes us up a little bit. So the first thing to do is get rid of the complex number at the bottom. And guys, the way we do that is we multiply the top and the bottom by the conjugate of the bottom. If I multiply this by the conjugate, then when you multiply it out, you're actually going to get rid of these i's. Okay, they're going to cancel out. Well, they're going to turn into a normal number because you're going to end up with an I squared. Okay, so always multiply the top and the bottom by the conjugate of the bottom when you're dividing, by the conjugate of the bottom. Okay. Okay, I'm not going to go through any of this in like too much detail, okay? Again, like before, I'm just going to give you the background. This is a really, really important, these beautiful diagrams I've drawn, which I mean, look how beautiful they are. I'm so proud of them, to be honest. Hope you all enjoy. These very beautiful diagrams are super, super important, okay? Can I get a show of hands of who's seen something like this before, these kind of diagrams before?
Or into the chat, guys. Chat might be easier. Yes or no? Have you seen it? Yes or no? Into the chat.
Awesome.
Yep.
Okay, a lot of people
yeses.
saying stuff like this. Brilliant. Okay. These are your Argand diagrams, guys. An Argand diagram, fancy name, because what we're trying to do is we're trying to plot complex numbers. Okay. we can't really plot complex number as a normal way of a y and an x because we need there to be an imaginary part. Okay, and when we go to plot complex numbers on an Argand diagram, we put the imaginary numbers on the y-axis and we put the real numbers on the x-axis. Okay, for example, we have the number, and we have the number, come on. Okay, we have the number 2 plus 2i, right? I'm going to go to my number 2 on my real number axis, and I'll go to my number 2 on my I-axis. And there is my complex number 2 plus 2i. Okay, so this is the way we can plot complex numbers. Now, when we add complex numbers in this plane, or we multiply them, or we do all these different things to them, guys, we can use geometry to find where that complex number is going to end up without having to do the mathematical part of things. Okay, which is really, really handy. It's really nice to conceptually know, like, okay, where is this going to end up? And it's something that comes up a lot in the Leaving Cert, right? Is they'll ask questions like, you know, they'll show you an Argand diagram with a bunch of you know, complex numbers dotted in it, and they'll say, you know, which one is z1 plus z2, which one is z2 times 4, right? That's something that comes up really, really often, right? And if you know these diagrams, it's really easy marks, okay? So just to quickly go through them, you can go through them yourself in more detail. The first one is that when you add two complex numbers, they form a parallelogram into the answer. When you multiply it by a real number, if you multiply it by 2, it stretches, right? Here's z, here's 2z. If you multiply by a number less than 1, it shrinks. If you multiply by a negative number, stretches off in the other direction, okay? If you multiply a complex number by I, rotates 90 degrees in the anti-clockwise direction. Now, here's your challenge, okay? If you choose to accept it after this call ends, using these 3 rules, right? How then, what happens if you multiply 2 complex numbers? What happens if you multiply 2 complex numbers? Well, let's have a look quickly, right? If I'm going to multiply this out, I'm going to go 2 by 2i, and then let's go minus 4i by 1 minus 2i. If you treat this as your z, guys, then you've multiplied z by a normal number, a real number. You've multiplied z by a real number, and you've also multiplied by I. And you already have a bunch of rules to show you how to do that. And you also know how to add 2 complex numbers. So see how you get on with that, okay? Okay, polar form of complex number. What is this about? How do people find the polar form, turning things into polar form in the chat? Do you find it hard? Do you find it fine?
Polar form, oh, Niamh, polar form is every second year, no? In the
Every
exams.
second year.
It comes up so often, right?
Oh, okay, sorry, that's what you were saying every second
No,
year.
I'm always trying to explain it's important, right? How often does it
Oh,
come up?
it's so important. So important. Yeah, absolutely. Absolutely. So important. It's just another way you can express a number. Because believe it or not, you can actually express all numbers in this kind of polar form way, right? But we only talk about it when it comes to complex numbers in the Leaving Cert. Super important, right? Let me just show you what the hell is actually going on here, right? Let's say if I again, I'm going to take this number a plus ib, right? It could be whatever. It could be 1 plus, you know, 3i, whatever. Who cares? Or I've got one here, e.g. 2 minus 2i. And I plot the real part here, a, and the other part here, b. Now, if I want to write it in polar form instead, I draw a line from z down to the origin, and the length of this is my or. The length of this is my modulus. And then I find what the angle is, from this line to the x-axis, and we write it in that form. And the reason that this corresponds the exact same way is because this is just forming a right angle triangle. This is literally just forming a right angle triangle. So if you think about it, cos theta is our a part of the formula. That makes sense because we have, sorry, my thing is freezing a little bit here. I'm just gonna give it a second. Sorry. This distance a, okay. Sorry, it's freezing again. Okay. This distance a, if we use a bit of trigonometry, okay, this is our adjacent side of our triangle. A over our hypotenuse, in this case is or, is just equal to cos theta. Equal to cos theta. So A is equal to or cos theta, just multiplying up by that or. Sorry, teacher, I'm having a bit of trouble with my OneNote is crashing. I might need to just
Okay, yeah,
go out and go in.
Just reshare. I haven't.
Yeah.
The cos form, yeah, you probably should get it right again, Niamh. But yeah, polar form into the killer. You're fine. It's just probably the.
It's just a lot of people on the
refresh.
Zoom.
Should be fine.
1 second, guys.
Polar form, yeah. I myself. I should get the deck as well. 2 seconds, guys. Get this right.
It's coming up now.
Nice. Give everyone a breather. You can grab a
Yeah,
side.
everyone take a breather.
Take a breath.
Yeah.
It's 44. We'll give a half an hour teaching. Is that right, lads? And then we'll go into the tests, okay? Just for context, another half an hour. Calculus, polar form. And what else are you hoping to get done, Niamh?
A little bit of trig as well.
Trig. Okay. I'm going to send you the notes and recordings and solutions to the tests. So it'll all be there. All right. Is there anything you want in the, if you want to chat there, any particular topics you want, like extra that I'll send you in an email? Anything? Like I've got these TikTok style videos, chat it to me there. Anything you want in particular? Function, trig is needed. Nice, Julia. Anything else, lads, in the chat? Logs. Yeah. Hate logs. Functions, line and circle, trig, probability, surds, constructions, logs, indices, logs. Oh God, people don't like logs.
Guys,
Trig and
I've got a bunch of YouTube videos up and coming with constructions and proofs, so you can check all that out.
Nice one. Back in business, Niamh, yeah.
Yeah, back in business. Okay, guys, so sorry about that. So basically
your red is hard to see, but that's all, but it's fine. We can get through
yeah,
it.
thank you. Let me just okay.
Perfect. Thanks.
So guys, do you see the where were we? Sorry. So basically what I'm showing you is right, okay, let's just get this really just quickly nailed, right? What I'm showing you is that when we're writing it in polar form, just using a little bit of geometry, if you turn this into a right angle triangle, okay, this side A over or, which is adjacent over hypotenuse, equal to cos theta. Therefore, A is equal to or cos theta, and that's why we form it in that way. You can do the exact same thing to show that B is equal to or sine theta, okay? That's all. That's where it comes from. Let's just make sure that we know how to actually write things in polar form. Let's make sure we know how to find them. So first things first, we need to find our reference angle. Guys, to find your reference angle, you're going to do the tan of the modulus of B over A. Okay, let's just use our example 2 minus 2i here, okay? Therefore, we're going to have tan of 2 over, I said minus 2. But again, we're taking the modulus of it. We're ignoring minus signs, but tan 2 over 2, which same as saying tan of 1, and that's just 45 degrees. Okay. The next thing we should do is we should identify the quadrant that we're in. So 2 minus 2, right? Well, we've got 2 on the x-axis, but then we've got a minus 2 on the y-axis. So it's in the 4th quadrant here, guys. Okay, it's in the 4th quadrant. Okay. Next thing is that we're going to find our argument. Guys, to find your argument, you can use this grid, right? This table is going to tell you for each quadrant how we find our argument. Okay. So for our 4th quadrant, we have that the argument is going to be 360 minus the reference angle. And we found our reference angle to be 45 degrees. So it must be 360 minus 45, which is 315, guys, right? I think. Last thing we should do is we just have to find our modulus. So it's going to be or is equal to square root of a squared plus b squared. So it's going to be square root of 2 squared plus minus 2 squared. That's just equal to the square root of 8, which is what, 2 root 2. Okay, so the polar form of our complex number, root 2 cos of 315 plus I sine 315. Okay. Now, this is going to be really important for what we're going to do next. Something that you see come up every so often, and it really throws a lot of people, is finding the nth root of a complex number. There's a couple of things we need for this, okay? Nth root of a complex number, we need to write, first of all, we need to write in polar form, but not only polar form, we need to write it in general polar form. Hands up if we've, or into the chat, who's heard of general polar form of a complex number? Sadly. Yes. Okay. So the general form of complex number, right, is when you write, okay, yes, cos theta or sine theta, whatever, plus n 360. And n here, guys, can be any natural number. It can be 0, 1, 2, 3, blah, 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 whatever. Okay. The reason for it is, right, let's just go back to our diagram of what a complex number even is in polar form. It's just some line in this plane with this angle theta. If I add 360, if I add 360 degrees or 2 pi radians to this, I end up in the exact same place. If I add another 360, all the way around, I end up in the same place. Again and again, again and again and again and again. Okay. So if I add 360 to my degrees, or if I add 2 pi radians, you end up in the same place. So general forms of complex number is saying, oh, well, you could express it as cos theta, but you can also express it as cos theta plus n 360, where n is anything. Okay, just take into account for every way we can write it. The other thing that we really importantly need to find the nth root of a complex number, de Moivre's theorem. De Moivre's theorem, guys, again, you do have to be able to prove this. And just mentioned before, but I'm currently working on a series of videos where I'm going through each proof on your Leaving Cert syllabus and each construction, and you can find that on the Breakthrough
I'll actually send in the video after, because that's really handy. Every proof and construction in one video in like all a minute long. It's actually really nice. I'll send it after, all right?
Yeah. They're by the way, they're not completely finished, guys. Give me a couple of weeks and they'll all be up.
There's enough
They're on
there
their
to
way.
keep you going.
There's some there though. You can start with them. Okay, so here's de Moivre's theorem. De Moivre's theorem says that, right, if we take, like, for example, let's say we had 2 minus 3i and we put it to the power of 5 or something, that we'd be there all day trying to multiply this out, guys. It would take us ages. But if we can write it in a polar form and we put it to the power of n being anything, n could be 6, n could be 200, n could be 1, then this is the same as saying or to the power of n by cos of n theta, it gets multiplied by the angle. It gets multiplied by the angle plus I sine n theta. Again, it gets multiplied by the angle. So important. So important. Okay. So using these two things, guys, we're going to try and do this question. Guys, everyone, pen and paper, let's all give it a go now. Okay, I want everyone doing this question. If you get the answer, if you think you've got it, set it in the chat. Okay. Now, but just to give us a bit of a head start, I'm going to straight away give us what z squared equals minus 8. Okay. So another way of thinking about this is z is equal to minus 8 plus 0i. Okay. I've already shown you how to write it in polar form. So just to save us a bit of time, I'm going to give us this in polar form, which is 8 cos 180 plus n 360, because again, we want to do it in general polar form, guys, plus I sine 180 plus n 360. Okay, I'm just writing this in polar form. If you were to find out what this is in polar form, we'd use the method that I just went through. Okay. All right. So we've been told that z cubed is equal to minus 8 plus 0i. So z cubed is equal to this whole thing. Now, if you got a z cubed and you want to find z, what should I do to both sides? If I've got a z cubed and I want to find z, what should I do to both sides? Amelia, go on, give it a go.
We haven't done that chapter yet.
Well, what about anyone, right? Put in the chat, guys. Anyone. Doesn't matter about complex numbers, right? If you had a z cubed and you wanted to find z, what would you do to both sides? Power to put both sides to the power of 1/3. Well done, guys. Both sides to the power of 1/3. Put everything to the power of 1/3. Our 3 cancels with our 1/3. And guys, now we can use de Moivre's theorem. Now we can use de Moivre's theorem. Okay. Okay, I can't get my white pen back. Hold on. There we go. Okay. So de Moivre's theorem said that we have or to the power of 1/3, so we do 8 to the power of 1/3. And then that we take our power and we multiply our angles. We multiply it by our angles. So we end up with cos 1/3 times 180 plus n 360. 1 second. There we go. Plus I sine a third times 180 plus n 360. Okay. Okay, guys, so we're going to multiply everything through by our third, and we're going to end up with, well, 8 to the power of a third is just equal to 8 to the power of a third is just equal to 2. End up with cos of 60 plus n 120, right? Plus I sine 60 plus n 120. Okay. If we started with z to the power of 3, how many answers should I get for z? Into the chat, guys. How many answers should I get for z? If I started with z cubed, how many answers should I get for z? Good. 3. 3. Well done. Guys, if I had z to the power of 6, I would need to have 6 answers for z. If I had x to the power of 15, I should have 15 answers for x. If I have x squared, quadratic equation, 2 answers for x. Okay, so the next thing is I need to now take what I just found and I need to turn it into 3 answers. I need to now turn this into 3 answers for z. How are we going to do that? How are we going to do that? Someone put in the chat. What are we going to do? I've got this thing, right? 2 by cos 60 plus n 120. I sine 60 plus n 120. How am I going to turn this into 3 answers? We're going to change our values for n, guys. We're going to change our values for n. So we're going to use n equals 0, n equals 1, and n equals 2. Okay, because remember I said you can change n and the actual value doesn't change because you're just going round and round and round and round in a circle, right? It doesn't really matter. So let's change our values for n. So for n equals 0, we get 2 cos 60 plus I sine 60. N equals 1, we get 2 cos 60 plus 120, 180 plus I sine 180, etc. Okay, you're going to do the same for n equals 2. Okay, how do we feel? Can we get into the chat if that makes sense? Roughly. Okay, I hope good. I hope good. Okay. Just something someone said actually was that someone mentioned briefly was logs actually, and I think that would be a really good thing for me to quickly talk about because trig is actually, I would love to spend more time on talking about trig with you, and if we do have time I will, but there's actually a lot of similarities between trig and complex numbers. A lot of what we did there actually really covers a lot of what you do in trig as well, okay? And I will also have the notes for those. But let's just talk about logs for a minute. Like weird thing, because, and this is why it's so weird, is because we're told like, oh, here's a button on your calculator, use it. What the fuck is that? Like, why is no one telling you what
does
it
anyone
is?
understand logs in the chat? Can you give me your feedback on logs? Is logs a killer? Like, does anyone understand logs in the chat? Anyone get it? A base? No, horrible.
Horrible.
Yeah, hate it. Yeah.
Never did. Okay.
If you never did it, it's gonna come up.
Yeah.
Yeah, it's a killer.
Like, yeah, here's the thing with logs. The reason it's so confusing is because someone has told you that this button, you just should press this button on your calculator and no one's told you what it is. And I just want to spend 5 minutes trying to tell you what this actually is. Okay, what is a log? Let me tell you what this is. I really hope this demystifies some of this stuff for you. Here's all your algebra topics, guys. By the way, I've given a couple of example questions and you can go through those in your own time. Okay, here we are, infamous logs. Okay, here's the point of a log, right? If you have an exponential equation, for example, you've got y is equal to 2 to the power of x, right? There's your exponential equation in pink. A log is an inverse of an exponential equation. So if you have, whenever you have a function like this, and often you're told in a question, oh, can you find the inverse of that function? So then instead of it saying, fx equals y, you end up with a function that acts like f of y equals x. It basically just like takes a function, just like flips it upside down. It just creates the exact equal and opposite function. That's what a log is to a exponential. If an exponential function looks like this, an exponential function never really touches the x-axis. It just gets like really close, but it never touches it, and then it flies up to infinity. And a log gets really close to a y-axis, And then it just kind of goes gently off in the positive x direction. Okay. Now, what a log actually is a graph. It's a function. It's just a graph. When your calculator is calculating values from a log, let me just look at it for a minute. When your calculator is calculating values from a log, encoded in the calculator is this graph, is this function. Okay, that's why there's just a word and there's no maths for it. Because the thing is that what we often forget to like teach is that maths is just as much about pictures as it is about letters and numbers. Okay, you don't always have a perfect, beautiful letter number equation to describe something. Maybe sometimes it's better described by a picture, and a log is this picture. This green picture, that's a log. That is a log. Every time your calculator takes a value, it takes a value from this graph. Okay, that's what a log actually is. Here's the absolute bread and butter of logs. Here's the most important thing to know about logs. How to get from a log to an exponential. Okay, what is it? It's the inverse. Again, it's the inverse of it. If I have a to the power of c is equal to b, then it's the same as saying log to the base a. Okay, your bases stay the same. Log to the base a is equal to c. Log is equal to the power of c. And I've described this really badly. Let me start again. Log to the base a. The base is the same as the base in the exponential. Okay. The power of the exponential is what it's equal to, and what it's of is what the power is equal to. Okay. I think it's frozen. 1 second. Here we go. So it matches up like this. The way I like to remember it, guys, is that the bases stay the same. The base of the log is the same as the base of the exponential. That's really important. And then I always think of it as, well, the power is what it's equal to. Okay, the power is what it's equal to. And the rest will just come then. Okay, now something that's really important to know about logs, you need to know all your rules, guys. They're all on page 21 of your log tables. You need to know how to use them. You need to know how to apply them. And we're going to come back, if we have time, I might just come back and do this question showing you that. But here's the thing I want to tell you about logs. Here's why logs are so useful, right? In real life, when we're using maths and whatever, engineering, physics, whatever. This is why logs are super, super useful. If you have your unknown in a power, if you have, for example, like some kind of equation that's like, 3 to the power of x equals 250 or whatever, and you're trying to find x, that's whenever logs come into their own, because you can use a log to take that power down. This comes up, I think, like at least every second year, if not more. At the part 1 or 2 of a big long question in logs, it comes up every single time. I was going through this with one of my students the other day, and I was like, oh, let's just go through all the log questions now that we've done it. And it was just this question over and over and over. It's the point where we're like, should we just move on? Because there's nothing different coming up. It's the same thing coming up every single time. And this is what it is. Okay, here's an example of one. This is from an old paper. The number of bacteria in the early stages of growing colony of bacteria could be approximated using this function. Whatever, a lot of words, there's your function. Where t is time, colony starts to grow, n of t is the number of bacteria. Okay, find in time, in hours, that it takes a colony to grow to 790 bacteria. Okay, so let's just sub that in. So we're told we're trying to find t, the thing in the power, ding, 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 logs, okay. And we're trying to find out whenever the bacteria is equal to 790. So I'm going to let n of t equal 790. Sorry, you're probably all like, what is she on about? But stick with me. I'm about to get to a really cool point. 790 is equal to 450 by e to the power of 0.06. I'm frozen again. 65 t. Okay. The problem is, guys, the unknown is in the power. This is a really, really hard thing to solve if you don't have logs. Logs has this really cool rule where basically if you have the log, let's say whatever, log to the base 2, doesn't matter, of x cubed, for example. Does anyone know what is that? What's another way that we could write this? What can we do with that power? If we've got a log like this, what can we do with that power? Into the chat, guys. What can we do with that power? Yes, awesome. So nice, guys. Well done. This can be brought down in front of the log. can be brought down in front of the log to give you 3 log to the base 2 of x. Another one, right? Log to the base 10 of y to the power of 7 is the same as saying bring the 7 in front. 7 log to the base 10 of y. Another cool thing about logs, right, is that let's say if I have, let's say 15 equals, 20 to the power of x, whatever. Okay, this doesn't exist, I don't think, but let's just give it a go. Let's say I want to take this x down in front. Whatever I do to one side of the equation, guys, I could do the other side of the equation. Okay, and the equation stays the same. So let's say I take the natural log. Natural log, guys, is just log to the base e. Okay, it's just a handy one because it's a button on your calculator, right? Take the natural log of both sides. Do ln of both sides. Then what happens? I've got ln of 15 is equal to, well, this x has to come down now because it's a power, x ln of 20. These things are just numbers, guys. They are just numbers. So you will end up with x is equal to ln of 15 over ln of 20. Okay, let's try one more. Let's try one more. I'm going to give you one. I want you all to give it a go. Let's say we have let me get my pen working. Hold on. Here we go. Let's say we have 350 is equal to 2.5 to the power of y. What is my first step going to be, guys? Get into the chat. What's my first step going to be? What can I take of both sides? What can I do to both sides? Take the natural log. Sick. So good, guys. Loving these responses. Take the natural log of both sides. Take the natural log of both sides. What's going to happen to my y? What's going to happen to my y? Guys, it's going to come down in front. It's going to come down in front. I'm going to end up with ln 350 is equal to y ln of 2.5. These are just numbers, guys. These are just numbers. So you then divide it through like you would like a normal problem, normal algebra problem. If I want to get rid of a ln 2.5, I divide both sides by it. These are just numbers. A log of a number is just a number. And we've got y. Guys, how do we feel about that? How do we feel? Can I get a show of fake hands? Are we feeling a bit more? You can tell me in the chat if you're like, Niamh, that just literally did nothing. Logs still suck. Did that help a little bit? Because these logs, this kind of question comes up constantly. This is like every fucking year. It's the same thing. Okay, good. Definitely helps. Okay, it's really helping my ego. Kind of helped. Okay, not that much. Okay.
Good.
So guys, just a quick thing, right? Just on these notes that we're going to send you, this is exactly from an exam question. You're going to do the exact same. Oh, what's happened? Sorry, I've lost it. Hold on.
You're okay, Niamh? Yeah, all good.
Bear with me. Can you guys see my screen?
Yeah, I can. Yeah, all good.
Good. Okay. I want you to try this. Use the exact same method, guys. This is part 2 of an exam question. Comes up all the time. All the time. Okay. TJ, how much time do you think we have? 5-10 minutes.
7 minutes past 7. That was great in logs. That was super. Do you want to do trig next? This is like get into the teeth of it. The test will help everybody, but if we did the test at 20 past 7, half an hour, just get stuck in. Like this is gold, and they're leaving certs, and you probably want. Do you want to do next? Trig? Is everyone up for trig next? Is that fair? Everyone do trig in the please, yes. Yes.
Right.
Yes. There's a lot of yeses for trig.
Off we go.
Okay, nice.
Okay, guys, trigonometry. There's a couple of things I want to say actually before I even get into this. Let's just talk about a couple of things. Trigonometry, the big things that are difficult, right? We got all the geometry sides. The geometry side is more like shapes, angles, stuff like that. Not going to go through that today. There's formulas, log tables. The main reason I'm not going to go through that, practice. Fucking practice. Really practice those questions. Just get used to picking things out. Another difficult thing in trig is you have to do a lot of like manipulations. Where when I say manipulations, I mean it'll say show that cos of 2a is equal to something like that. Again, That is practice, 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 practice. It is one of the most difficult things in your exam, I would say, is rearranging those things. And the way that you do that is you just practice it all the time. Have your log tables open, play around. Don't be afraid to get it wrong. Leave it for a day, come back again, try again. Leave it for another day, come back again. And if for the third day you haven't got it, okay, you can look at the solution. But give it that time. Give it that time, because when it clicks, oh, satisfying. So good. Okay, so give it the time. What I'm going to talk to you about today is the kind of unit circle part of trig, right? Where you get questions that are like, sine theta is equal to 1/√2. What's theta? And you kind of have to look at the unit circle, and it's similar to stuff about complex numbers, right? That's the kind of stuff I want to talk to you about today. If I can find it, that is. Yeah, okay. Let's do it. So guys, I have this here, page 16, geometry side of things. Yeah, other thing is a lot of trigonometry proofs, you need to learn them. They're also coming up on YouTube. I've some up already, but there are more to come. Okay, let's talk about this unit circle thing. I'm sure we've all seen this before, right? This kind of thing that says in this quadrant, sine, cos, and tan, on the first quadrant, sine, cos, tan are all positive. Second one, sine is positive. Third one, tan is positive. Fourth one, cos is positive. What is that all about? Okay, well, let's just take a second to actually just explain this. Let's say that I have, let's say my angle is in the second quadrant, for example. Okay, here's my theta. The reason we say that sine, cos, or tan is positive or negative, right, is all to do with this. Okay, imagine angles coming out in each of these quadrants. We're going to focus on the second quadrant, okay? The opposite of this angle is in the positive y-axis, so it's about, let's say it's 3, who cares? But the adjacent side, this side, the adjacent side, is actually like at a minus, because this is a minus x-axis. Okay, so this is like, I don't know, -4 maybe. So say if I went to take, the hypotenuse is always positive, so say it's about 5, whatever. Say if I went to take the cos of this now, the cos of this angle, well, I'd have that cos theta is equal to adjacent -4 over hypotenuse 5. And we end up that the cos theta is a negative number. But let's say, what if I want to do sine theta, guys? Sine theta, the opposite is 3 over the hypotenuse 5. It's a positive number. It's a positive number. This is what this is about. It's about creating right angled triangles in all the quadrants and then just seeing if they're positive or negative. Okay? That's all that is. That confused me so much in my leaving cert. Really confused me so much. That's all this is. Okay? Okay. So there's a couple of these questions, right? One way they do it is they say sine theta is equal to 1/√2, for example. And you have to find theta. The other one is you have find cos 210 in third form. Okay, and then you have to find what the cos theta is equal to, or the sine theta is equal to. I'm going to show you both of these now. Okay, for a question like this, first step, find the reference angle. Again, similar to our complex numbers, we are ignoring the minus signs. Okay, so to find your reference angle, guys, you're going to do sine -1 of the modulus of this. If there was a minus sign in here, guys, we just ignore it. So sine -1 is just equal to 45 degrees. Or if we have people that are more inclined with radial with radians, it's going to be pi/2, pi/4, pi/8. Okay, so now we need to mark in what quadrant that this is in. Okay, we need to mark in the relevant quadrant. So how do we do that? Well, we see that this sine theta is positive. So what quadrant is sine theta positive in? I'm going to call some random person, Andrew McGrath. Andrew McGrath, what quadrants is sine theta positive in? Andrew, maybe he can't hear me. Katie May, what quadrants is sine theta positive in? Okay, I'm like, give it a go, guys. Come on, give it a go. Okay.
And
oh, nice. Yes,
yeah.
Katie?
Is that all in sin?
Yes, good. So it's the first quadrant and it's
Yeah.
the second quadrant. Awesome. So good. Well done. So good. Well done. So the first quadrant, it's the second quadrant. So good. Now, guys, this is only our reference angle here. Okay, this is our reference angle. So to find our theta, we now need to use this table, right, to tell us this table of formulas to tell us what our theta is. In the first quadrant, well, it just stays the same. So we have it's 45 degrees. In the second quadrant, it's going to be 180 minus theta reference, which is going to be 180 minus 45, and that is just 135. Yeah, 135, right? Okay. Cool. So then you're done, guys. That's it, right? You said solve sine theta equals 1 over root 2. Well, you found that theta is equal to 45 degrees. And theta is also equal to 135 degrees. Now, what if it was the exact same question, but it was actually said sine 2 theta is equal to 1 over root 2? Okay, this one has a couple more steps. Okay? So I'm going to let you continue on this question as if it said sine 2 theta is equal to 1 over root 2. What I do is I let 2 theta equal to 45 plus n360 and 2 theta equal to 135 plus n360. Yet again, guys, if we add n360 or if we add n2 pi, if we're thinking in radians, we're just going around the circle. Just go around the circle, you end up at the same place. Okay, you can always add 360, you can always add 2 pi, end up at the same place. What do we do here? We divide through by 2, guys, because we want to get rid of this 2 in front of our theta. We're trying to find theta. Divide by 2, we end up with theta is equal to 45 over 2, that's what, 22.5, is it? Plus n 180. And we have theta is equal to 135 over 2. What is 135 over 2? I don't even know off the top of my head. I'm going to leave it as 135 over 2 plus n 180. Now, because there was a 2, this is so important. This is so important. Okay, everyone hear me. Because there's a 2 in front of our theta, we need 2 answers for each of these. Because there's a 2 in front of our theta, we need 2 answers for each of these. If there was a 5 in front of our theta, we need 2 answers for each of them. So because of that, we're going to do n equals 0 and n equals 1 for each of these. So for n equals 0, we just have 22.5. For n equals 1, we've got 22.5 plus 180. For n equals 0, we've got 135 over 2. For n equals 1, we've got 135 over 2 plus 180. Okay, let me just stop there. Do we have any questions so far, guys? How are people feeling? Are we a bit lost? Hands up if you're feeling all right.
Or into the chat, lads. How you getting on? Good, bad, shout, text us, chat, all good, bad. We've got 5-10 minutes left. Good, few goods, shaky, nice. Shaky is a good way to describe how you feel before the mocks.
Shaky's a really good way to describe. If you weren't feeling shaky, I'd be worried.
Lost, confused, few people confused. Yeah, fair enough. Okay, that's no hassle.
Okay, guys. So the last one, if we're going to do the exact same thing, we're going to flip it around. And this time we're going to do our cos 210 insert. I'm just going to rub this out so we can actually see what we're doing here. Okay, this is our question. Find cos 210 in surd form. All right, here's a big hint for you straight away. If you're trying to find cos 210 in surd form, I mean, straight up, you're not going to type into your calculator and give them the second answer, right? It's like the whole point is they don't want you to use your calculator. They actually want you to use, there's a page in your log tables that gives you like cos 30, cos 40, cos 45, cos 90, and for sine and tan as well. And it gives you those in surd form. More often than not, you're going to be doing questions that involve those angles 30, 45, 90, because they're the ones in your log tables and they don't want you using the calculator for this at all. Okay, so they should be those very basic angles that are in your log tables that you should be getting out. Okay, and if you don't, maybe go back of your work. Maybe something's gone a bit wrong. Okay, first step to do this question, mark the relevant quadrant. Okay, so just a quick thing, actually, can I just say quickly? if you're so confused, like, it's grand. I promise you it's grand. The point of this really is that you go over it again, is that you listen to this again, okay? So if you're confused, like, I really wouldn't be surprised at all. It's so normal that you would be. Okay, mark the relevant quadrant. 210 degrees is going to be somewhere down here, guys. Okay, this is about 210 degrees. So we're in our third quadrant here. Okay, so we want to find the reference angle. So to do that, we use our grid, we use our code, and we end up with that theta. So theta is 210 minus 180 is our reference angle. So that's going to be 30 degrees. There you go. We've got a 30-degree coming out. This is what's in our long tables. We're on the right track. We want to determine the sign now. Okay. So in the third quadrant, is cos positive or negative? That's the question. Is cos positive or negative? Well, we have all sine t cos, so it's negative. So we're going to have the cos 210 is equal to minus cos 30. And that's all going to be equal to minus. Now cos 30 is in your long tables and it's √3 over 2. Okay, and those are those two questions, guys. Okay, that was a lot. That was a lot of information, and you all did very, very well to stick with me as long as you did. But really, what I'm saying is, when you go through this notes and when you listen to these recordings back, that's really what I want you to do, because to pick up all of that in this amount of time, that's a lot for sure.
Well done, Niamh. Right, super. I'm going to launch a little poll just for my own interest. How do you get on? There's a test coming, so just take a breath.